is obviously quite a popular subject because we have a very large number of attendees. So when we do the question and answer session at the end, if we run out of time, my email address is at the end, so please feel free to send me an email with your questions and I will respond and get back to you. So with that being said, we'll get started. And as I said, today's session is on the importance of having a good safety requirement specification. And clearly this is an area that is of very much relevance and also important to a lot of people. But before we get into it, I just want to tell you a little bit about Exida. Exida is a global company. We've been around for the last 16 years or so, and we specialize in three main areas. We specialize in functional safety, cybersecurity, and alarm management. And of course, the three, in our opinion, are very tightly linked and very relevant, not just to any one particular industry, but is what we like to call industry agnostic. So therefore, you can apply this to the automation, automotive, process, and nuclear industries, and we've worked in all of those. And we've worked with manufacturers, helping them with their certification of their products or their development life cycles, and also their competency development. The same with the system designers. We also provide tools to support them, and the Excellencia tool, I know, is known by quite a lot of people, and it's a full safety lifecycle tool. And we're very excited to say that we're bringing out a new version of Excellencia that should be available in the second quarter of this year. We also work with the end users on the full safety lifecycle in terms of supporting each of the phases and helping with developing competency and providing tools, and the same with the engineering contractors. So we've worked with all of these companies that are in these areas, and also provided support on the three main disciplines, which is the functional safety, the cybersecurity, and the alarm. And interestingly, cybersecurity is becoming much more relevant, and as we shall see later on when we talk about the life cycle, the new proposed life cycle that's coming out will have more emphasis on the cybersecurity side as well. Exida has also authored and written a lot of books and papers, and we have a lot of these available through our website. We also provide a lot of information free of charge. This is one of them, the webinars that we do each week. We have blogs, we have white papers. So I encourage you to visit the website. Also, these webinars that we do are all recorded, and they're available via little YouTube videos. So they're archived and they're available on the website, so you can go and find many topics on functional safety, cybersecurity, and alarm management. From the certification point of view, we are accredited by ANSI. We do provide both product certification for functional safety and cybersecurity now, and we also run personnel certification programs through our CFSE board. A little bit about me. I've been around in industry now for nearly 39 years. Started life as an electronics design engineer and was designing products for ESD, emergency shutdown systems, fire and gas systems, and addressable fire systems in the late 70s, early 80s. And since then, I've moved on into more of a sales role, etc. But for Exida, I wear many hats. One of them is to be a trainer. I teach the functional safety engineering course, the FSE 100. I've written papers, and also I manage the cybersecurity and the functional safety end user business. So that's a little bit about me, but let's move on and talk about the main topic now. So safety requirement specifications. Safety requirement specifications, the reason we have them is because of this. if you look, the HSC, the Safety Executive in the UK, did a study initially in 1995, but then updated it in 2003, looking at the causes of accidents involving control systems. And interestingly enough, you can see here that 44% was specification. So this was either a poor specification, wasn't defined properly, and also 15% was design and implementation. So not only was it not specified properly, it wasn't designed and implemented properly either. So that was an interesting statistic. And since then, we've had the IEC 61508 standard come out and the IEC 61511. And the purpose of the IEC 61511 standard was to provide a framework where you could provide a consistently reliable and safe design for safety instrumented systems. And effectively, the standard has three main phases. There's what we call the analysis phase, where if you're looking at the process hazards, you're looking at the current layers of protection that are non-SIS, and then you compare that to the amount of risk reduction you're looking to achieve with your corporate risk criteria. And then the remainder has to be done either via safety instrumented system or some other means. And if you're using safety instrumented systems, then you have one or more safety instrumented functions. Each safety instrumented function is designed to handle a particular potential hazard and has a target safety integrity level, or put another way, it has a target risk reduction that you're looking to achieve. So of course that is important, because what you have to do is convey that to whoever is going to be doing the design of the system. And this is where the Safety Requirements Specification comes into play. And of course the thing about the 61511 standard and the 61508 standard, they're what we call non-prescriptive. They will tell you this is what you need to do. They won't tell you how to do it, such as a prescriptive standard will tell you this is what you need to do and this is how you do it. So you do have flexibility, you do have options to be able to achieve the goal. And the goal, of course, is to design a system that provides you with sufficient reliability and integrity to be able to meet the risk criteria that you're looking for. So the objectives here are to build a safer system that don't experience as many of the problems of the past. Hence, going back to that 44% figure that we had for poor specifications being the result of accidents. Of course, if you do it right, you build more cost-effective systems. So you're now matching your risk and design in a more cost-effective manner. And the other thing to do is to eliminate weak designs that obviously cost much and provide little. And as I mentioned earlier, you need to have a consistent framework so that you can provide repeatable designs. And the whole point of doing this is, one, we want to avoid systematic faults, and two, we want to reduce the potential for random faults. So in other words, we want to increase or we want to improve the reliability of our system. And systematic faults, of course, for those that aren't familiar with systematic faults, these are insidious and can only be really eliminated or reduced through good design, through processes, through training competency, and having all the procedures in place, doing proper testing. And this comes back to the fact that you need to have a good process in place. Shell did a study as well and looked at some safety lifecycle successes, and interestingly enough, what they found were that 49% of safety functions were actually over-engineered. So you can get too rigorous and you end up being highly conservative. And if they're over-engineered, they can potentially cost you more. The good news is that only 4% were under-engineered, but there's still 4%. and 47% had no change. So again, the point of following the safety life cycle is to make sure you end up with a cost-effective design that meets the risk reduction criteria you're looking for. So from the Safety Requirements Specification, the point here is that it should be a specification that contains all the requirements of the safety instrumented functions in the safety instrumented system. So when we talk about a SIF or the SIF requirements, we're looking at what do we need to be able to do the detailed engineering, and how do we convey that? Well, for each SIF, what we need to convey is firstly the functional requirements. What are the actions, the function actions, how should it work, what is it going to do? And then secondly, we have to specify the integrity requirements. And here we're looking at the specification of the risk reduction and reliability requirements. In other words, here's where we define our target SIL. How much risk reduction are we looking to achieve from our design? And of course, this is how well it should work and how quickly it should work. Because again, what we're looking to make sure is that we can run quickly enough to be able to avoid the potential hazard. So this means that you need to understand the timing requirements for the system and the process. So here, process safety time is important to know and understand. And the whole point is that usually this is a document that's produced and is given to a third party, another company, to execute. Typically this would be an EPC, or it could be an integrator, a systems integrating company that's putting it all together, putting the SIS together with the BPCS. So you have to remember that this will be interpreted by somebody else. So of course, that's in itself going to open up potential for what we call systematic issues again. So we look at the life cycle. Here we've gone through our analysis phase, we've identified our hazards, we've looked at our consequence analysis, we've identified our protection layers, and now we're looking at the probability of failures for our likelihood analysis and LOPA, and that then determines whether we need further risk reduction, and if we do, are we going to require a safety instrumented function, or are we going to do it another way? And of course, when we're looking at the safety instrumented functions, we need to select the risk reduction factor that we want for each of the safety instrumented functions. And of course, this is from the process point of view, where we would be in demand mode applications or low demand, in which we would not be expecting to see a demand on the SIF any more frequent than once per year. And from that, we then come into developing our process safety requirements specification, what we call our process SRS, with our conceptual design. And you'll notice there that it says IEC 61511 Stage 1 FSA, which is a functional safety assessment. So at this point, we should be verifying or validating at least that the SRS has included all of the previous steps and that we have dotted all our I's and crossed all our T's. In the current 2003 61511 standard, this stage is optional. However, in the new standard that is due to come out this year, they are now going to make the 5 functional safety assessments that are specified as mandatory. Currently, in the 2003 standard, only Stage 3 FSA is really mandatory. The others are just recommended. So having got this, we know that the SRS has to provide us with all the information we need to properly design, engineer, and implement our safety instrumented system. So this includes what the process information is. What's the hazard information? What hazards are we trying to avoid and prevent? what are the frequencies that these occur? And again, what are the consequences? And from which we have a target SIL that we need to meet. And then any regulatory requirements. There could also be, if some companies, some large corporations have their own particular requirements that they need to meet as well. So this would be, for example, if you're operating in offshore, you may have some API, you might have NFPA in other areas, you will have 61511, 61508, there might be some OSHA requirements, etc. And from all of this, we end up with a functional requirement and an integrity requirement. So each SIF needs to have a functional requirement and an integrity requirement. And from that, you end up with a hardware and software conceptual, and then a detailed design. And then you do the validation. And from this, we end up with our system, our safety instrumented system, and the correct procedures. So it's not just a case of providing the design information. You need to make sure that how are you going to test it? How are you going to maintain it? So this is where proof testing is important, and the proof test procedures have to be well defined. Because again, if you don't spend the time during the operation side of things to properly perform the maintenance at the required intervals that are defined here in the SRS, then your integrity is going to be diminished. So this leads us from analysis into implementation. And then we get to our operations, maintenance, and modifications. And this is where we go to operations. So those are the three phases. And those of us are old enough to remember the old adage of 20-20-20. We used to say 20 weeks in design, 20 months in implementation, and 20 years in operation. So clearly, most of the time it's going to be spent in the operations and maintenance. And therefore, the SRS is not just a once and done document. You just don't do it once and stick it on a shelf somewhere. It is a live, it needs to be a live working document. So you need to reflect back. If any changes or modifications are made, those have to be assessed from the safety point of view, and then they have to be fed back into the SRS. I can't tell you the number of times I've been on site and I've asked to see drawings, and if the drawings existed, they were never up to date. There was never the as-built. So clearly, when you get into the operations and maintenance side, management of change is very important, and so changes need to be reflected back into the SRS. It's very important. So of course, what we're talking about here is communication, and communication can mean different things to different people depending upon interpretation. And of course, if something is vague and ambiguous, it's open to interpretation. So for example here, this is how the customer explained it. This is how it was sold. This is how it was designed. This is how it was built. And this is how it was tested. And my favorite one of all is, this is how it was documented. And I imagine some of you are probably chuckling about that, because we've all seen how bad documentation can be once things get out into the field. This is how it was installed. And of course, this is how it was built. This is how it was maintained. And this is what the customer really wanted. So it's very important to make sure that you define your requirements as clearly and concisely as possible, with little ambiguity and little room for interpretation. So as a living document, it needs to be the correct point of reference during the operation phase. And in fact, the standard says that whoever's doing the maintenance of the SIS and its SIFs, they need to know what each SIF and the SIS is protecting against. They need to know what are the overrides, the bypasses, the interlocks. They need to know what the maintenance requirements in terms of what proof tests need to be run and when. And don't forget that the SIF is not just a single piece of equipment. It will consist of sensors, it will consist of the logic solver and a final element. And each of those will have different, potentially different proof test requirements in terms of the frequency, and they'll have different proof test requirements in terms of testing. And the thing about the proof test, which mustn't be forgotten, is the proof test is not just to say, yes, it works. The proof test is to try and find potentially dangerous faults that any automatic diagnostics can't find. So here again, the SRS needs to be constructed so it's clear and free of jargon, and avoid TLAs, i.e. three-letter acronyms, wherever possible. If you do have TLAs, then make sure there's a glossary of terms and those are well defined so people understand what you mean. Be concise, basically don't waffle, use bullet points wherever possible, keep the English simple, don't have too much repetition. It needs to be complete in terms of the two requirements that we said for each SIF, which is a functional requirement and an integrity requirement, and any non-functional requirements covered as well. Needs to be consistent. Avoid the contradicting statements or requirements. That's very important. And as I mentioned earlier, once we get into the operation and maintenance side of things, any changes need to be evaluated. So, for example, we know that during the mission time, which could be 15 years, 20 years, we know during that time technology is going to move on, manufacturers are going to make certain equipment obsolete, and you will probably have to go back and replace. Of course, if you're going to replace, then you need to do the assessment to see, have I compromised the integrity of my safety instrumented functions? And the other thing to remember as well is, because this is a performance standard, we should be periodically, and again the standard doesn't define what periodically means, but we should be periodically going back and doing an assessment to say, are we obtaining the integrity level that we were looking for with our SIFs? Are we getting better reliability numbers from the feedback during proof testing and any maintenance that we're doing for replacement? Because if we are, we can maybe adjust the proof test intervals, and we can probably change the design. If the performance we're getting is much better than what we had originally intended. So the point there is that we have some key KPIs, some key performance indicators that we should be looking at in terms of, are we meeting our spurious trip rate? Is our mean time to restore actually what we said it was in the SRS, or is it much less, in which case we can modify? So the point there is you need to assess and what the impact is going to be. So from the functional point of view, we need a definition of the safe state, because the safe state may be don't do anything. We look at the process inputs and their trip points so that we understand what those need to be, the process parameters for normal operating ranges, and what are the outputs and their actions. We also need to define the relationship between inputs and outputs, as well as, are we looking at energized to trip, or are we looking at de-energized to trip? So if the safe state is an energized to trip, that needs to be defined. If the safe states are de-energized to trip, that also needs to be defined. And then, are there any manual requirements in terms of shutdown? So does an operator need to do this? If so, how? And the consideration of bypasses, do we have a redundant system or not? What are the actions on loss of power to the SIS? Now this is highly critical for energized to trip systems. And then what are the response times for the SIS to bring the process to a safe state? and the response actions for overt fault. What we mean by overt fault is a revealed fault. So in other words, if a piece of equipment fails, and if it's a redundant system, in a 1 out of 2, it could cause a spurious trip. So what do you do then? What's the operator interface requirements? Again, the operator, if he's going to be responding to alarms, and we're taking credit for that, he needs to be able to react quickly enough, so we need to define what we have to do there. And what are the reset functions? The other thing is the required SIL for each SIF. If we're looking at demand mode applications, then we should really be defining a risk reduction factor. Because if you say, I need a SIL2 SIF, and what you really mean is I need a SIL2 SIF with a risk reduction factor of better than 300, and don't say that, the designer could give you a SIL2 SIF with a risk reduction factor of, say, 110 or 120. It's a SIL2, but it's not going to achieve the amount of risk reduction you want. So you need to be clear about that. Then what are the requirements for the diagnostics to achieve the required SIL? Here again, usually manufacturers will give you some recommended proof tests with coverage. They may say that you need to configure the product this way to achieve a diagnostic coverage of, say, 90%, and based upon that, this will be what you need to achieve the required SIL. So you need to be aware of that. And to use another 3-letter acronym, I always like to say when I teach the class, it's RTFM, which is read the flaming manual. So in other words, read the safety manual, because the safety manual, if you're using certified products, gives you a lot of useful information and will tell you how to achieve, especially if it says capable. If it says this is a SIL2 capable device, you need to understand what does that word capable mean. So you need to read the safety manual to understand that, okay, you might need 2 of them, or you might need to configure them this way, or have the diagnostics set up this way. And what are the requirements for maintenance and testing to achieve and maintain the required SIL? Here again, manufacturers will give you, most of the time, a recommended proof test to achieve a certain coverage factor to maintain the SIL. You may find from your own performance records that you have a better way or you have another way to achieve higher coverage. So you may create a proof test based on that. Here again, this is all back to performance. If you're monitoring and checking your performance, you can make improvements. Reliability requirement if spurious trips may be hazardous. In this case, I mentioned the safe state may be do nothing. Some processes may be critical that if you stop quickly, the product or whatever they're doing may cause damage to the equipment. So the product may solidify and cause thousands of dollars or potentially tens of thousands of dollars of cost. In terms of structure, the best way to structure the SRS is with a general requirements section, so you have requirements common to all SIF, so you don't need to repeat it. And you might have, along with that, you'll have the SIF requirements, which are the individual SIFs, and have their functional requirements and integrity requirements. So as an example here, we could say that in this case, we're talking about all safety instrumented functions except fire and gas and special cases shall be designed such that the movement of the fire element at the safe position will be performed by removing power from the element. So here we're saying that unless otherwise specified, it's de-energized to trip. Fire and gas systems generally are energized to trip, or there might be cases where you need to start a motor or start a pump, which would be an energized to trip. And then SIFs that are not de-energized to trip will be clearly described in the individual SIF specification. So here again you'd say, all right, this is an energized to trip. And for safety functions, where energized to trip is selected, you need to make sure the piece of wire that's connecting it hasn't fallen off. So normally you would put some sort of monitoring circuit to make sure that current is able to flow to the final element to trip it. Here again, all safety instrument functions shall be designed in accordance with requirements set forth in the following statutes, regulations, and standards. So here you'd specify what are the common standards. 615.11, 29 CFR 1910 for OSHA requirements for process safety management, 40 CFR 68, for example, and there might be others, plus you may have some internal company ones. Those should be specified there. Unless otherwise specified in an individual SIF's logic diagram, the mean time to fail spurious of a SIF shall not be less than 25 years. Typically, we see this number, 25 years. It seems to be a reasonable. Some might have it slightly lower, but 25 years is typical. Unless specified otherwise for an individual SIF, the response time of SIF shall not exceed 3 seconds. Maximum response time for each subsystem operating asynchronously shall be shown below. So here again, you need to know for this particular SIF how quickly is it going to respond and how quickly does it need to respond. And what we're saying here for the final element is the 2 second. And I know that there are some final elements that are much slower than that. So again, you'd have to take that into consideration during the design. And then what you do is you specify against each particular SIF. You can see there's an ID. There might be a PID reference. What's the required SIL? In this case, it's a SIL 1. What's our test interval? In this case, it's 3 years. Response time, you can see that's covered by a general requirement. The activation method is a de-energized to trip, which of course is covered by a general requirement. There is a manual reset required, that's covered by a general requirement. And the nuisance trips, see general requirement number 4. What are we trying to do with this? Well, the service is a low recycle gas flow closes fuel gas to reforming heaters dropout valve. And the safe state in this case is the fuel gas to reforming heaters RH01 and RH2 is stopped by closing the fuel gas shutoff valve. See, that's from this you can see it's very clearly defined. It's clear to understand. Now, interestingly, we'd said SIL 1, but we haven't put a risk reduction factor. So if we want a low SIL 1, that's fine. If we want a risk reduction factor of at least 60 or 70, we really ought to state that. From the logic description point of view, there are several methods you can use. You can use plain text, which is obviously extremely flexible, doesn't require any knowledge, but it's time consuming, and here again, it has to be transposed to program code, so we could be introducing potential systematic issues if we're not careful. Cause and effects diagrams, again, low level of effort, and it's a good representation from a visual point of view, but it is a pretty rigid format, and some functions you can't actually show easily in a cause and effect diagram. So therefore you can oversimplify. Binary logic diagrams, those seem to be mostly the ones that are used. It's more flexible than the cause and effect, and it does give you a direct transposition to a function block diagram program. If you're using one of the 5 programming languages that are defined in IEC 1131, let's see if I can remember. There's instruction list, structured text, ladder, I think function block, and sequential function chart. Those are the 5. So here again is an example. If we say, if one of the following conditions occurs, switch BSO1 is de-energized, indicating loss of flame. Switch PSL02 is de-energized, indicating low fuel gas pressure. Then the main fuel gas flow to the heater is stopped by performing all of the following. You close valves 3A and 3B and open valve 3C. And the respective valves will be opened and closed by de-energizing the solenoid. So again, that's easy to understand and clear, but you've still got to transpose that into some sort of code. Cause and effect is much easier to see. Here you can see for the burner loss of flame, we have to close all 3, and of course for the fuel gas pressure low, we have to close all 3. If you're using a tool like Excellencia can give you gives you a cause and effect for the overall SIF, and Excellencia has an inbuilt SRS generator as well if you're doing the design. So if you've done your PHA and LOPA in Excellencia, you do your SIL determination, you can then do your conceptual design and your SRS. So it's very easy to use and do, and it can save hundreds of hours. Binary logic, most of us understand the binary logic, and I'm sure a lot of you on this have used this before, so you're very familiar with it. So in terms of summary, the SRS should have a general section which covers the SIS. So if you've got any non-functional requirements, those need to be specified. What are the regulations and standards? Failure in terms of start and restart. Bearing in mind, of course, that most of the problems or the accidents in recent time have been a result of either startup or just after maintenance. So startup is very important, and restarting. So if you've got a process and you have to keep restarting it because of spurious trips, you could be potentially increasing your risk. So it's important to have that well defined. What are the interfaces? Again, are you going to have OPC links? Are you going to have a connection to the process control network? Are you going to have any wireless interfaces? And of course, if you do, you've got to consider the cybersecurity side of things, because if you compromise the SIS because of a cybersecurity incident, that could increase your risk tenfold or more. What are the environmental conditions? That's another thing that's very important, because if the system is going to be going in, for example, on the north face, it's going to have a completely different set of environmental requirements compared to if it's going into the Arabian desert or even offshore. So environmental conditions are very important to understand and to be defined. From the SIF's general point of view, again, maintenance overrides. What are we going to do when we're doing maintenance? Do we have manual shutdowns? What's the operating modes? What are the failure modes? How can it fail? What do we do for reset, and what diagnostics are there? And so therefore, all the maintenance guys need to understand and know this. And that's why it's very important that the SRS just doesn't sit in somebody's office, that it's actually where it needs to be during operation, which is with the maintenance guys. So whether that's the mechanical integrity program manager, whether it's the process safety manager, or whatever, that needs to be available. And then for the SIF itself, the SIF specific, you need an identification of the SIF. What's the description or duty? Could be a P&ID. What's the safe state? What's the required SIL? And here again, if it's demand mode, I encourage you to specify the actual risk reduction factor. What's the proof test interval? And very important. And also, what's the proof test coverage? What's the response time? And here again, you need to know what's the process safety time. The architecture summary in terms of what sensors or sensors, logic solver, final elements. What's the voting arrangement? Are we looking at a 1 out of 2? Are we looking at a 2 out of 3, 2 out of 2 for sensors, logic solver, and final elements? What's the mode of operation? Is it energized or de-energized to trip? Are we in demand or continuous mode? If we're in continuous mode, then diagnostics have to run at least 10 times faster than the demand rate to be able to take credit. So that's very important to pay attention to that if you're looking at continuous. What's the trip setting and logic? What are our spurious trip requirements? Startup overrides and any other special requirements that need to be considered. As I've mentioned before, Excellencia does actually provide you with the capability of creating the process SRS and the detailed SRS. So you can do all your design in there, which is it's very useful. It saves time and it's consistent, and there are given templates. So everything's there for you. So what are some of the potential SRS problems that you can have? We see this, unfortunately, we see this quite a bit. We see that the hazard or the risk analysis wasn't done properly, so you end up with a HAZOP that's missing things, or the LOPA that's either taken credit for twice for something, and so this comes down to the fact that you need to have somebody who's extremely competent and knowledgeable and understands the process to be able to facilitate a PHA and to obviously conduct a LOPA. So if not, what you can end up with is misidentification of SIFs. You could end up with the fact that you either have SIFs when you don't need them, or you may be missing SIFs. And the other problem is you could have the wrong SIL level selected. So and that could be, if you need a SIL 2 and you've only selected a SIL 1, you're automatically increasing your risk. Not defining all the failure modes and protection requirements. Again, what actions do you need to achieve the safe state? If you don't define it properly, you might not actually achieve the safe state. And here again, adding in risk. The measurement might be too slow to pick up and prevent the accident. So again, if we're in demand mode, we need to know what our process safety time is, and also, especially if we're in continuous mode, we need to know how quickly the SIF needs to act. And diagnostics play an important role in both, but more especially in the demand mode application, in the continuous mode applications, where you need to have them running at least 10 times faster. In demand mode, you need them at least twice as fast as the demand would come in. So for example, if in demand mode, if you've got a 1-year demand, expected demand, you should be proof testing every 6 months. Not defining all operating regimes in terms of startup, shutdown. If we don't define it well enough, you could end up introducing potential risk during startup, which is typically the most hazardous time anyway. Not defining all the environmental conditions. You could end up in a situation where you haven't specified the correct temperature or vibration. I'll give you an example. Years ago, we did a system for a power plant in India, and at the time it was one of the largest diesel engine plants in the world. These diesel engines were 50 megawatts, and they were 10 meters high, or 30 odd meters high, 30 odd feet high, and there were 4 of them. And I remember going to the plant and standing outside with just 2 of them running, and the ground was moving. It was actually shaking outside the building, and when we went into the control room, it was even worse. Now, what we found was they hadn't specified a vibration requirement, and so what we ended up having to do was to put in rubber shock absorbers for our disk drives on our HMIs, because we had some problems with the HMIs, as you can expect. It wasn't defined. So you need to define the environmental conditions. The SRS is not maintained. Here again, poor revision control, and it's so important to make sure that if you make changes, that you analyze what those changes are for the SIS, and make sure that the SIFs are updated inside the SRS. Because if you don't, you're going to end up with potential problems, and again, you're adding risk. Conflicting or missing requirements, safety and non-safety actions. The standard is very clear about separating SIS and safety from non-SIS, in other words, from the BPCS. And we know from experience, we've all seen it, that there are systems that mix the two. I had an example where one client said he had 150 I/O in his BPCS and he had 120 I/O in his SIS. And when I looked at it, he had control, non-safety control in the SIS. So what he was doing was he was adding to his cost, because the safety requirement, the requirements for proof testing and maintenance on an SIS are much more stringent than they are on a BPCS. So how to avoid mistakes during specification of system. Here again, 1508 provides guidance. You have project management. There is a functional safety management requirement, and so you need to establish an organizational model and guidelines and procedures. So people need to be responsible for certain phases of the life cycle, and they need to know that they're responsible. It can't just be a name on a box in somebody's shelf as an organization chart. It needs to be defined, and they need to understand that. You need to have clear, concise, and complete life cycle documentation for every phase. You do need to separate safety and non-safety functions for the reason I just mentioned. You need to have a structured specification, and I'm a firm believer in checklists. And the analogy I use is the pilots. Every time a pilot gets in a plane, in a cockpit, even though he may have flown thousands of hours, he still follows his checklist to make sure he doesn't miss anything. And that ensures consistency. And then some semi-formal methods, logic diagrams, sequence diagrams, etc. So the quality of the SRS is not a measure of the thickness or the number of pages. It's actually how clearly and concisely it conveys the requirements to the reader. And that's very important, because that way you can avoid potential systematic issues and potential issues with having a poor design. So let's just summarize. We need a clear set of requirements to ensure the accurate and safe design of the system and its SIFs. So what we're trying to do is reduce systematic issues and at the same time reduce potential for random failures. We need to avoid jargon, and we need to keep the requirements succinct. So like I said, if you're going to use TLAs, three-letter acronyms, make sure you have a definition. Ensure that all the key maintenance personnel understand what each SIF of the SIS is protecting against. This is a requirement in the standard, but it makes sense to have the guys understand and know what it is they have to do. So competency and making sure that they're evaluated is very important. Because if you have an instrument tech that miscalibrates a piece of equipment but doesn't know he's miscalibrated it, the next time he comes to calibrate it, well, guess what? He's going to do it wrong again. Define the target SIL levels with specific risk reduction factor for demand mode. That's very important. So that will ensure that there's no over-design or under-design, because the designers have to show how they've met that risk reduction factor. Understand the response times, and so that you know that the thing will shut down safely within the safety time, the process safety time. And of course, run the proof tests according to the SRS is essential to maintain integrity. And maintain and update the SRS as part of the MOC. That's very important. Needs to be fed back. So that's it in a nutshell. And obviously, if you have any questions, either send them to me. Let's see if we've got, trying to read here. See if we've got, I can see I've got a lot of questions, so let's see if we can pick up some of them. Okay. Do we need to describe each SIF? Well, yes, you do. This is the whole point, as I was saying. Yeah, you can have up to 40 to 50 SIFs, that's right. And that's why, like I said, for a tool like Excellencia, it's very helpful, because you can easily create the SRS. But the standard is very clear. You need to define for each SIF its functional and integrity requirements. So an SRS, if you've got 50 to 100 SIFs, you could have a 200 or 300 page document quite easily. That's why it's very important to make sure that you define as succinctly as possible. Okay, what else do we have here? Well, there's a question about how do you prepare the SRS. Again, you need to, when you're doing your process SRS, when you're doing your initial conceptual design, this is where you start looking at what equipment do I need. And so therefore, like I said, this is an iterative process, and it can be very, very time consuming if you don't have a decent tool to do it with. But basically what you have to do is you have to go through, pick equipment. Here again, you can either use the SAEL list that we have on our exida website, which has all certified equipment under different categories, not just the ones that we've certified, but ones by other agencies. If we believe the numbers, we will put them on our website. So you can use those. And then what you have to do is, obviously, you've got to go through and do the calculation for each piece of equipment, because remember, of course, there are 3 barriers that you have to overcome to meet the SIL level. One is the PFD average if it's a demand node, or a PFH if it's continuous. The second is the hardware fault tolerance, and the third is the systematic integrity. So the standard defines what you need to do there in terms of requirement. Other than that, you have to go through and just do the iterative loop to make sure you meet the target. And here again, as I've said, if you're using a tool such as Excellencia, it makes life a lot easier, because you can, in Excellencia, it has the inbuilt failure rate database for each of the devices. So if you choose a device, it automatically populates the failure rate data, and it does it in real time. So you can do a design very quickly and model it and get the results straight away. Okay, what's the give and take? Yeah, one is, there's another question about not having seen an SRS before, and how do you give the results to the client? How many documents do you include, the math or only the results, etc.? You can, I mean, usually what we do, as I've shown you, with the printout of Excellencia, we have a model, we show a picture of the SIF, and we show the calculation results. In other words, what was the PFD average, we show that result, and what was the achieved SIL. Again, if you want to email me, I can send you a bit more detail on that. How can we achieve better risk reduction factor without reducing proof test interval and partial stroke testing with all diagnostic? Well, again, this comes down to the equipment you choose. Some of the equipment will have better. If you're using, say, failure fraction, you can. That's a good. If the manufacturer provides you with, say, failure fraction, that's a good way of going, because if you know if it's type A or type B, you can use the 1508 tables to look at what SIL you can achieve, and then using Excellencia, for example, you can pretty much work out what risk reduction factor you're going to achieve. How do we count this? Well, process safety time, again, that comes down to your process engineers and understanding what your process is, and obviously that's going to be plant dependent. How do you determine a SIL level target? The SIL level target, if you're doing LOPA, what I like to say is that what you're looking at is the event frequencies, how often is it going to happen? And so therefore your risk reduction factor remaining, once you've done LOPA, and LOPA is looking at your non-SIS layers of protection. If you've got your non-SIS layers of protection, you expect each layer of protection to give you at least an order of magnitude. So for example, if you've got 3 layers of protection that are non-SIS, you would expect to get a risk reduction factor of 1,000. Then what you would do is you would compare that to your target frequency from your corporate risk requirement. So if it's showing that you need a further risk reduction of 100 or more, then you know that that's going to be a SIL 2. So if you need a risk reduction factor of 115, then you need a SIL 2 with a risk reduction factor of at least 115 or better. And that's how you determine what you need. Here's another question. what does it say here? It's just, if a proof test in the SRS says, oops, I've lost it again, 1 year, but the designer needs to increase to 6 months to achieve required SIL to improve PFD, is this okay? Well, yeah, but you should ask why. I mean, that's one way of doing it, but obviously the equipment he selected isn't as good as what could be specified. But yes, that's one way to do it. You can do it, but you're adding. The thing to remember is you're trying to balance cost against requirement and maintaining the integrity. So obviously, if you're going to be doing more frequent proof testing, that can introduce risk in itself, but it also introduces cost. So you would have to balance out with maybe a slightly more expensive design can give you the benefit of going to a 1-year proof test interval, and compare that to having to do more frequent proof testing and the possibility of introducing, again, systematic issues by the fact that if the person doing the proof test isn't properly trained, they could introduce some problems. If we use generic failure rates and excellencia, how can we meet systematic integrity? Well, yes, there again, the systematic integrity, if you're using certified devices, systematic integrity is defined with the SIL. If you don't use certified devices, then you really don't know how the product was designed, what procedures the company's following, how have they tested it, how competent are their people. And generic data tends to be slightly more pessimistic anyway, but you as the end user would have, or the end user would have to sign off on the fact that the systematic integrity wasn't covered. What else do we have here? Is the new 615.11, sorry, in the new 615.11, who is responsible for the SRS review and the FSA? Is this the end user EPC or more towards the system integrator now? Well, the standard is very clear that you need to show independence, and so therefore you could use a third-party company like Exida to do that because that's fully independent. What they mean by that is you need to use somebody that's, number one, competent, and secondly, is not associated with the design in any way. So again, those are the two requirements, and the new 15.11 is going to put a lot more emphasis on competency. And in fact, I've been told there's a lot more shalls in it than there was in the other one. Do we need to include inertia time at the pumps in calculating? Yes, of course, because the pumps are going to be part of the SIF. Much of the time, the maintenance and testing requirements aren't known until the SIF has been designed, so it's not something we can specify up front. Well, that's where the detailed SRS comes in, because in the detailed SRS you've done the design, or at least you've done the design on paper. And if you're using excellencia, of course, you would have all this information. So you would look at the for each of the devices used, there would be a recommended proof test from the manufacturer. If not, then you would have to use your own experience, or you'd have to define proof tests to give you as reasonable high-level coverage as possible. This question is quite a long question, so this involves, because we're almost out of time, this involves, it says, using other documents to support, SRS could be in an index document, using other documents to support LOPA report diagrams, SSRS with LBL language, PLC, how much detail is required in the software requirements beyond enforcing that the software enforce the functional requirements of the SIF. Well, here again, you have to put as much information as required to achieve the functional requirements. yeah, you can refer to other documents, and the SRS could be more than one or two documents, but the point is you need to have it all together in one place, because, like I said, you've got to be able to maintain it. So it has to be transferable to the operations and maintenance team. Okay, we're out of time, and I've still got a stack load of questions. Please use this email address to email me the questions that I wasn't able to get to, and then what I will do is I'll be happy to send you a response. I hope you found this useful. This is recorded, so it'll be available probably in the next day or so on the website. And it's being run again this afternoon and again in a couple of weeks. So I thank you for your time. I thank you for your questions, very good questions. And please feel free to contact me with any further ones. So with that, I will sign off and wish you all a good day.